So I sort of touched on the spare receptors. This comes back to the spare receptors. Let's consider that we've got 4 drugs, and this is a picture out of Goodman and Gilman. I tried to soften the text a little bit and clarify it a little bit. But let's say drugs A, B, and C all work at the same receptor, A, B, C, and D. They have different degrees of intrinsic activity, and they can all produce the same maximal effect. So this will be a system with some spare receptors. Let's say the number of filled circles represents the number of receptors you need to occupy by that drug to get the effect. So drug A has to occupy all 10 receptors to get the maximum effect. On the other hand, drug D, even though there are 10 receptors there, only has to occupy 1 receptor to get that maximum effect. Why? Because it has higher intrinsic activity. D has higher intrinsic activity than A. B and A are about the same. They both have to occupy and activate all 10 receptors. C is sort of in the middle. It has to occupy 50% of the receptors, but 50% can be unoccupied and you'll still get the maximum effect. So in terms of intrinsic activity, D is going to be given the value of 1. It's the highest. C will be given a value of, I don't know, point whatever it is. If 50% spare receptors, it'll be 0.2 probably. And A and B will have even lower intrinsic activity. Yeah, question?
What about the KD for those?
The KD can be varied across those drugs. It does not have to be the same. Because KD isn't going to be related to, once you bind, they have to have a KD value that's reasonable. Let's put it that way. They have to be able to bind for this analogy to work. But they don't all have to have the same KD. They don't have to have a KD that's within, 1 log unit of each other and those kinds of things.
So it doesn't mean that KD of the drug B is higher.
This has nothing to do with the ability. This has nothing to do with the ability to bind to the receptor, except that they all have to bind to the receptor. But it doesn't say you have to bind really avidly, have a low KD, or have a high KD. You just have to be able to bind to that receptor. Drug D has really high intrinsic activity. We'll give it a 1. C is intermediate, and A and B are even less than that. But they can all produce the same effect if you're measuring some outward effect. Why? Because there are a whole lot of receptors that would be called spares. So A and B must activate all the receptors to get the maximum effect. There are no spare receptors in this example. But you can still get the maximum effect with this drug because there are that many receptors out there. Drug A may not have it's not going to have the intrinsic activity of C or D, but it can still, in the end, when you net it out, it binds and activates more receptors, although each receptor is activated at a lower level. The mathematical product of that is essentially still going to be the big effect. Drug C can get the maximum effect with only 50% receptors occupied. So there's 50% spare receptors for drug C and 90% spare receptors for drug D, because it can get the maximum effect and a whole bunch of receptors sitting out there saying, what about me, what about me? And they're not needed. Question?
Max effect is when we've used all the receptor messengers.
Yeah, in this, and that's one way that you'd have that maximum effect, yeah. Yeah.
Mr. Gator, that drug B is going to be the full agonist of the partial agonist?
Yes, you're exactly right. So her question was, so drug D is a full agonist with intrinsic activity of 1, we'll say. Drug C is going to be a partial agonist with lower intrinsic activity. Drugs A and B, even lower intrinsic activity than C. So we're going to give them some scores there. Yet they can all produce the same maximum effect. Why is that? And this is the picture you're going to get. And this is why spare receptors can be important. So this is essentially the left half. I've already shown you this. This is the effect that you can get with a drug with a full agonist, the blue line, intrinsic activity of 1, partial agonist, intrinsic activity of 0.5, weak partial agonist, intrinsic activity of 0.1. If there are no spare receptors, obviously you get a bigger effect with the blue line than with the red or the green. On the other hand, if you have spare receptors, in the example we showed you, with drug C, you can actually get a full response, full maximum response with that drug, even though it's a partial agonist. And you can get a bigger response with drug A, although it doesn't go to the max in this case, with spare receptors. And this is the 50% example, this is not a 90% spare example. Yeah?
So spare receptors are really only a factor for agonists, not inverse agonists?
Spare receptors will be, the question was, is this only agonist and not inverse agonist? Spare receptors are going to come into play for both agonists and inverse agonists. I didn't show you the inverse, but that can be also come into play there. The real issue is that spare receptors come into play only with partials, whether it's a partial agonist or a partial inverse agonist. If it's a full agonist, you don't get a very dramatic difference between a situation with spare receptors and not spare receptors. They have the same maximum response. The point here is, again, we're trying to say what's going to determine the effect of the drug. We got one thing that we can all agree on, very quantifiable, very cool, KD. The drug binds to the receptor, we measure the affinity as a KD. Low KD values mean higher affinity. KD is defined as the concentration that binds half the receptors. That we're cool on. The stuff that's a little more fuzzy is the stuff that comes into play when you're trying to determine the effect of the drug, and that is, what's the actual intrinsic activity, and we use an arbitrary scale, full agonist 1, full inverse agonist -1, antagonist 0, things in the middle, and then we look at the potential for spare receptors. We're not, in most cases, in most cases that you're going to run into, there's not going to be a quantitation of how many spare receptors there are, and so this partial agonist will produce this effect relative to this full agonist kind of thing. But you will see that come into play on occasion, but it's less quantifiable. The quantifiable piece is the affinity of the drug for the receptor, KD. But the other two will come into play when you're looking at what does the drug actually do. So we've got all four of these. All three come together to give you the efficacy. You've got to bind, and that's your KD, that's your affinity. Affinity, KD, is the concentration where you bind half of the receptors. After you bind, you got to do something, or not. If you're an antagonist, you don't do anything, you just bind. But if you're a full agonist, you're +1. If you're a full inverse agonist, you're -1. If you're partial, you're in the middle. So that is a part of what's going to end up leading to your ultimate effect. Another part of that is there receptor reserve, and what's the magnitude of that receptor reserve? And that will come into play as well. And all of those will lead to essentially the post-receptor response. What is this drug going to do? And it's going to do it because A, it binds, 2, it does something after it binds, and 3, maybe there are spare receptors. So that's quantitation.